All right, good morning everyone. Welcome to today's lecture. Today we're going to talk about texture mapping. So we're moving a little ahead in the book because this is something that you need also for the practicals. So we're skipping a little ahead. So let's just motivate this by quickly looking backwards. What we've done so far, we started with introducing vectors and used them to describe some geometric objects. We talked about how we can calculate intersection with those objects. Also by directly calculating them, but also by using matrices, for example, to calculate the intersection of planes using linear equation system. And last week we also talked about how we can use matrices to do transformations, vector transformations. And also at the very beginning we talked about shading, where we introduced this very simple shader model or shading model. So with all this, we can already do quite a lot of things. We can use the vectors, for example, to represent points. We can use, for example, 3 points to represent a triangle. We can use matrix multiplication to transform this triangle. And we can use our simplified shading model to put some color on these triangles. So, for example, if we have the normal vector here at the vertices of the triangles, using the light vector L and the I vector E, with which we look at the points in the direction of the eye, we can calculate the color of the vertex at this of the triangle at this vertex. But of course, we also want to have color between those vertices. And this is an example from an image from the first practical. Of course, if you put this into the system, the API automatically calculates this color here. But of course, we're also interested in what goes on behind it. What is actually the function doing? How is this function implemented? That gives you this kind of color here. And what it does is it uses something that is called linear interpolation, because we have different color values at different vertices of the triangle, and in between we interpolate between those color values. And this is done by using this linear interpolation equation, which is, you can think about it as a weighted sum. So you have here 2 vectors, and then you multiply them with a weight, 1 minus t and t. So a weighted sum, similar to, like, if you look at the on the website, the conditions to pass this course or the final grade is calculated by 2/3 of your exam grade plus 1/3 of the practical grade, so a weighted sum. So you're familiar with this, and you also see that the weights add up together to 1. For the grading, it's to make sure that the final grade, even if you have a 10 in both, you will not get a higher grade than 10, which is why the weight also makes sure that it is stays within that range. If we do it with vectors, of course, the weight guarantees, if it sums up to 1, it guarantees that we get the 1 vector. If we have that we have in the extreme cases, we have vector A or the vector B or any vector in between. So you can think about this as a weighted sum, but you can also think about this in terms of geometry in a different way. If you transform this, if you write it that way, that you have A minus TA plus TB, then you can write this in the form A plus T, B minus A. And I hope that this looks familiar to you, because that is exactly the definition that we had of the parametric equation of a line. So if we think about this in a way that we have here our vector A and here our vector B, then we have A as the support vector of the line, and B minus A, this vector here, is the direction vector of the line. And if you remember, in the first tutorial there was an exercise where we were talking about, if we choose the support and the direction vector that way, what does the value t represent on the line, or how can we get to a point on the line by modifying the parameter t. And if you remember it, if we had t equals 0, we became the support vector. If we had t equals 1, we became to the position of the direction vector, and everything in between was the related fraction between those. So if we had, for example, t equals 2/3, like we have here in the image, then we come to this point here. It doesn't want me today. Here we go. So, yeah, so you can see also that you can interpret it in this way. So what we can do with this, we can, by modifying the parameter t or continuously increasing it, we can smoothly create all vectors on that line between A and B. Or if we interpret our vector as color values, we can smoothly interpolate between two different color values. So if we see the vector as a color, Ci is the red, the green, and the blue value of it, then we can take this here as the color values, and then we can smoothly interpolate between the vertices. So here we interpolate between the vertices here, here, and also of course here. But of course we also want to have color within the triangle, but we can also do this by linear interpolation while we are walking along this vertex here, along this edge here. While we are walking along this edge here, we can also interpolate between 2 points here in the same way by doing a linear interpolation, and then we get this smooth transition of the colors that you saw in the image before. So this is pretty simple and pretty straightforward, and we'll see later in the lecture how we can implement this efficiently and also how it relates to other kinds of shadings when we talk about more in details about shadings. But for now this should be enough. So we see here that we can create triangles, how we can put color on those triangles, and of course the triangle, if we make the triangle significantly small, then we can model all kinds of things with it, so we can create some very realistic images with it. The problem is, of course, if we have a very complex structure, a very complex image, in theory we could model this with very small triangles. So for example, if we have this wooden structure here, then we can make the triangles by making the triangles small enough. We could, of course, model this with triangles, but it would not be very efficient to do this because, first of all, it would be very hard to do it realistically because the pattern is not really regular. So we have a very chaotic structure here because each single part of the wood looks a little bit different than the other part. And also, even if we would do it, it would be very computationally expensive. It would require a lot of effort. So doing this by triangling with triangles and coloring triangles will not work very well. So, but if you look at this photo actually looks quite realistic, and that is the idea of texture mapping, that we use a photo and paste it onto an object, or we use in general a texture, paste it onto an object, and then create a realistic image by that. And one of the approaches, for example, is we could take a small image like that and tile it, and then we get a bigger image. Now, of course, depending on what kind of image you take, you can also get some regularity. So, for example, here you see, probably not that much at the beamer, but if you look at the slides later in the printout, you see that each second tile looks a little darker than the other one because we have this regularity. Also, I made it actually on purpose that they are not really directly connected to illustrate the tile structure, but if we put them closer to each other, you see that we can get quite a realistic image of that if we choose an appropriate texture for it. Good, so this technique is called tiling. Good, and that is of course the basic idea of texture mapping. We say instead of explicitly calculating the color for each point, we just take a structure, a texture, and paste that onto an image, onto the object, like an image that we glue on an object. Of course, this texture does not necessarily have to be an image. It can be all kinds of structure that we can use, and so we are distinguishing between two different approaches here. One is the 2D mapping, which is also called image textures because 2D resembles an image. So we basically we take a 2D image and glue it or paste it onto a 3D object. And the other is called 3D mapping, where we have a 3D texture. So we have information about each point in 3D, about the structure, how the structure or the color looks like, and then we can map that, of course, also to a 3D image. And the intuitive illustration of it is, in one case, of course, we take an image and glue it onto an object, so it's like gift wrapping, and the other is like carving something out of an object. So we have like a structure, like in this case, the marble structure, and then we carve an object out of it. Good. So we're dealing with 2D and 3D textures. Now be careful, don't confuse this with the 2D and 3D objects. Sometimes I'm also explaining it with 2D objects because it's easier to explain in 2D, and then I switch to 3D. Here we're dealing with 2D and 3D textures, and of course we can also apply 2D textures to 3D, like you've seen here in this image. And so be careful not to be confused about this here, because now I'm also going to talk about 2D and 3D spaces, because in 2D it's sometimes easier to explain, and of course sometimes we're also dealing in graphics with 2D spaces. Yeah, so let's start with 3D texture mapping. So this part here where we have this situation here that we have some 3D block of a texture and want to map that onto an object. So how can we do this? Well, one approach, or this kind of approach, is usually called a procedural approach, because how we do this is that we actually do not really glue an object, glue a texture onto an object, but we take the object and we calculate use a procedure or a function to calculate the color value of a point on that object based on this texture. So, for example, here on the teapot, we look at the point here. So this is our point P, X, Y, Z. And then we take that point, or XP, YP, YZ here. And then we take that point, put it into our function, and then a function gives us a color value. So that's pretty straightforward. We just need a function that encodes, that allows us to calculate this color value. And that is, of course, a difficult part. So the question is, what kind of functions, or what kind of textures, what kind of patterns can we create with these functions, and how would such a function look like? Now, if you look at this simple example with the stripe pattern, this is actually a quite simple function that we can use for this. So let's look at this example here where we have the stripe pattern along the x-axis. So this is the x-axis here, and we have the stripe pattern. So you see the stripes on the teapot change along the x-axis. And for that, we can use this function. So we take a point here, xp, yp, zp, and then we check, is the sign of the x larger than 0? Then we return one color, like, for example, red. If it is lower than 0, then we return white. Now, if you look at the sign function, you see, of course, this gives you directly this stripe here, because every time you are above 0, you get red. Every time you're below 0, you get 0. And since the sign is a periodic function, this gives us this alternating values for the stripes. Of course, sign is a one-dimensional function, is a function from 1D to 1D. But if we turn in all the 3 values, and then for any y and z, we just look at the x value, of course, in the y direction, we get a stripe pattern like this. And if we look at it in 3D, then, so if we have here y, x, x and z, then we get these 3-dimensional blocks of red and white alternating. And then, of course, if we calculate it for a random point P here in 3D, if this is our point P, then we get the appropriate value, either red or white. So yeah, this is pretty straightforward. And of course, we can use any kind of alternating function. So for example, we could also say we can take the integer part and then check if of the x value, and then check if it is odd or even, and then return red or white. So it basically just has to be an alternating function. Good. And of course, we can also do this for the other teapots. So for example, for this teapot here, where we see we have alternating stripes along the z-axis, we could use this function where we just replace the x here with the z value, and then we get the same here. So in 3D, we also get here this three-dimensional block. So if we put in a point in that 3-dimensional space, into this function, we get the related color value from that block here. So pretty straightforward, and also for this teapot, I'm pretty sure you're able to figure out how we have to change the function here to get this texture here on the teapot. But of course, we do not only have to cannot only create patterns where we look at one coordinate, but we can also look at 2 or 3 coordinates at the same time. So for example, we can also say we define a pattern by saying it returns one color if both the x and the sign of the x and the set value is larger than 0. So let's see what we get then. In the first case, x is larger than 0. Like I said, that's the case we had, where we had these stripes here. Set larger than 0, that's the second case we had. Now if we combine this, if we say both have to be larger than 0, then we get the intersection of them, which is something like, oh no, that was not it. It's exactly not it. This here. So we get here these squares. Nothing here, 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 here. So you see we get here this, yeah, in 3D, of course, these are then these bars. So we get some blue or red, depending what color we take, bars here. So we see we can create this square pattern on our teapot. And that actually looks already quite like a checkerboard pattern. And if you're wondering why I'm mentioning checkerboard, then I want to let you know that the deadline for the practical 2 is approaching soon. So this is something you have to do for the practical, to create a checkerboard. And I'm not going to tell you how it looks like, but if you look at this image and if you look at this condition, and if you follow the logica and remember what you have to do, then it's pretty straightforward, I think, to know, to figure out how to change that function to, or change that procedure to achieve a checkerboard pattern here. The other thing you might want to change for the practicals is, of course, because of the way I was drawing it here, I did the z and the x-axis. But if you take the y-axis, like they did in the image, where you have the x and the y aligned with your screen, then you will probably also want to create the checkerboard not in the x-z plane, but you want to probably create it here, like this. So you get a checkerboard pattern when you look at the teapot from the front and not from the top. It would also be a nice exercise to do it in 3D, that you get a checkerboard from all different kind of sides, but that's not asked in the practicals, if I remember correctly. I think that's a question in the tutorials. Good. So another thing you want to change, of course, for the practicals, when you want to create a checkerboard, you do not necessarily want a checkerboard that has, where the tiles have a width, a fixed width, which in our case is pi, because here you see the because of the sine function, of course, the width here is p. So if we want to have that with a random width, we have to scale it by a factor width, and that is done by this function here, where we take the sine, not of x, but of x times p divided by the width. So you might wonder now, if I want to scale something, so for example, if I want to make it twice as large, why do I have to divide? Do I not have to multiply? But if you look at the sine function, how the sine function is defined, so this is the sine of x, this here is the width p, and this is the wavelength 2p. Now if you want to have, if you look at what happens if you have sine x, let me check, sine 2x, then of course the wavelength reduces by half, so you get a wavelength of p. And if you look at the sine of x divided by 2, then you get, of course, twice the wavelength. So if you see, if you want to increase the width, you have to divide the x by it, and likewise if you want to get rid of the p, then you have to normalize it. And usually when you normalize it, you divide by the maximum length. But here you have to divide the x, which means that you have to divide by width divided by x, which means the y comes to the top, which means y you have a multiplication here. Good. All right, let's look at another modification of it. So we can create this stripe pattern, but then we have fixed stripes. So a variation of this would be that we could say we want to have a smoother transition between the colors. So we do not want to have this binary black or white or red or white, but we want to have like a smoother transition like in the image at the bottom. And we can do this if you remember what we talked about at the beginning, the linear interpolation. When we have two color values, we want to want to have a smooth transition between them, we can use linear interpolation. Now if you look at this procedure, you see here that this is pretty much or this is exactly a linear interpolation between a weight. But of course the question is, what kind of weight are you choosing? Because if we choose the linear weight like before, then we get this very regular transition. So if you look at it right now, for at the top we have, if this is our x value and these are the colors C1 and C2, then we have this binary decision. Here we have the color 1, and then we have the color 2, and then we have again the color 1, and then again the color 2. And this is, of course, the width of our pattern. Now, what we could do is a linear interpolation. If this is C1 and C2, that we say, okay, we gradually decrease the fraction of the color 1 and increase the fraction of the color 2. And then again here. So this means basically if we have a t here, then this is the part of t, and this is the part of t minus 1, and that is then the fraction of the color 1 in our combined color value. Now, of course, this gives us a nice transition here, but it's still quite regular and gives us these strict changes here. So if we want to make it a little smoother, what we could do is we could use the sine function here to get the value for the weight. So what we do here is we take the sine function, but we want to have a weight between 0 and 1, but the sine is between 1 and minus 1. So to scale that, what we do is we move the sine function. So the sine is like this. So what we do is we move the sine function up by 1. That's this here. And then of course we are between 1 and 2, so we have to scale it by a factor of 2. And then we get exactly what we want, which is between 1 and 0, a sine function. And then we can use that here for our, oops, that was not nicely drawn, but you get the idea, for our color values. And that way we can create this nice, smooth transition here. So you are welcome to try this at home or in BBL 175. So I think this is actually not part of the practicals, but you are welcome, of course, to do it. But I think this one is part of the practicals, with the checkerboard pattern, not with the stripe pattern. Good. All right, so we've seen now that this is a way how we can create a 3D pattern or 3D texture by defining a function that allows us to calculate the appropriate color values for that particular pattern. And this is why we call this a procedural method, and this is also why we call it volumetric or solid texturing, because we're looking at a volume, a texture represented by a volume. But of course we do not only have to always need to specify a function to calculate this, but we could also say, if we already have an array, for example, a designer created it or we have pre-calculated it somewhere, why should we calculate each time these values? Why do we not just store them in a 3D array and then just look them up? And this is called then the array lookup technique, where we take a 3D array or a 2D array, and then we just take the coordinates from the points and look at them, the related color values in the texture. So the question here is, how do we map the point in 3D to a position in our 3D or 2D array. So the array lookup is, if we have a 3D texture, then we take a point here and then we look into the 3D array, and then we have to know, okay, which point do we have to look at here. Or if we take a 2D, for example, we could say, like we did a kind of comparable to the stripe texture that we had, where we were just looking at the X value. If we just have a 2D texture, we can just look at the XY value of the image and then look at the 2D image or the 2D texture, where is a related point to the color value to that, and then put the color value on the 3D position on our 3D model. So this would be a 2D lookup. So let's start with the 2D lookup because that's easier to explain, and then later we'll see that this generalizes straightforward to the 3D case. So what we have here our space in which our object is defined, our 3D object, or in this case 2D because we're ignoring the third coordinate. And here we have our texture. And what we need is we need to map a pixel from our coordinate space, which is often called in relation to texturing the UV space, from our UV space to a point on a texture, which is often called a texel in relation to pixel. So a texel is a texture pixel on the texture. It's just a point there, but it helps to explain it, to use this terminology. So we have here, for example, our object, for example, a triangle, and we have a point here. And now we want to look up in a texture the color value C at the position ij. So this is pretty straightforward mapping problem, and this is actually quite simple mapping problem if we do what we often do, which is restrict our space here to 1, to our values here to be between 0 and 1. So you remember what we wanted to do is we wanted to have this tiling here. So we want to map this texture here to a tile here, and this tile, we define this as having the length of 1. So all the values in between are between 0 and 1, and then we map them to this texture here, and we can get these values here by just removing the integer, by just removing the integer part of the UV axis. I was looking for this here. So we say we take for a value here, for example, here we have 2.2, here we have 1.2. So we get this, we scale this to the tile by just removing the integer part. So this point here becomes 0.2, 0.2. And that means, of course, we have the same value here, we will get the same color value when we look it up here, because we map the tile to the texture. And that is, of course, exactly what we want, because we want to reproduce the texture in a tiled way. So we have this value here, and we get this by using this so-called floor function, which is the function that just basically gives the highest integer value. Wait, there is something. Oh, no. Oh, sorry, I mixed up two things. I combined two steps. We're doing the tiling. That's why I had to look at this first. We remove the integer part to get the tiles, and then when we have the tiles, we have to do the mapping. So we have to map this from 0 cross 1, from 0 to 1 side to an x and an y here. And this mapping is pretty straightforward because we are between 0 and 1. So we just have to multiply it with the width and the height of the texture. So for example, if we have here 0.2, then we multiply an x times 0.2 times an x, and then of course we get here to the same relative portion here that we would get in the tile here. And that way we can easily do the mapping. The problem is, of course, because we have here values between 0 and 1, and here we have an array, and use this ij as an index into that array, we need integer values, of course, to look into that array at this index position, but when we do the mapping, we will not always get these index values, but we will have comma values. So what we do with this, how we deal with this, is we use the so-called floor function, which gives us the highest integer value. So it basically throws away the values behind the comma, and that means we then get the ij value here. So if we illustrate this in an image, we get from the UV, we get a pointer to a position here, which with the floor function is not always an integer value, but if we then throw away the value behind the comma, what we get is then this color value here, Cij, that is at the bottom left corner of this square that we are in with our pixel. And then we can use that color for that pixel on that object. Now, of course, the problem with this is that all points that are in here will be mapped to that color here, because that is the lowest integer value that we get. And this is actually, I think this is wrong. This should be like this here. In the book, this is also mentioned once, I think, as the nearest neighbor interpolation, although I think the nearest neighbor interpolation would be that you say, you split it, and then of course here, if you are here, this is the nearest neighbor, so you map this here. But in both situations, you get the same problem, which is that all values within one square here are mapped to this one color value. And here, of course, you have all the values within that square mapped to that color value, which means that in your image then the texture has some could have some artifacts, because you have some very abrupt color changes at the border. So how can we deal with this? Now, if you think about what we did at the beginning with the stripe texture, when I said we have this binary change between the color and want to make the transition a little smoother, we thought about doing a linear interpolation or this interpolation with the sign, the weights that depend on the sign. So the solution here is to make it smoother is, of course, to use some interpolation between the color values. So we could use a linear interpolation. The only difference here is we have 4 colors because we're in 2D. So if we are select the point here, we have 4 corners around. So we need to interpolate between 4 colors because we're in 2D. We need 2 weights, whereas in 1D, when we interpolate between 2 colors, we only need 1 weight, which is why we have a linear interpolation. Here we have a bilinear interpolation because we need 2 weights. And this formula looks a little cryptic first, but if you look at it, what's there, it's actually pretty simple. We have the 4 color values, and we have a value an index ij here, and now we want to interpolate between those color values. So we take the color values and sum them up, and multiply them with some weight, and then we sum it up. And the weight now is this bilinear weight, and that is, like you remember in the linear case, we had t and 1 minus t. Here we have u dash and v dash and 1 minus u dash, 1 minus v dash. If you look at the image, this u dash is defined as the value that we get from the scaling minus this integer part. So this is the part after the comma, which means that these are also, of course, values between 0 and 1. So that means that this here is y dash, this is 1 minus y dash, this is u dash, and this is 1 minus u dash. Now, if you look at what happens here with the weights, if you look at this point here, the closer this point is to this color, to this vertex of the square, the Cij, the larger this weight 1 minus v dash and 1 minus u dash get. The closer we get here, the larger these 2 values get. So the larger this weight here, that means the larger this impact of this color value is on our total sum. And this weight, the v dash and u dash, gets smaller if this gets closer to here. So the influence of this color value here gets reduced. which is, of course, makes sense, because the closer we are to a corner, the higher should be the influence of that color on the point that we put in this, the color that we put on this point here. And also for the others, we see it's the same way. The closer we get here to this value, the larger 1 minus u dash gets, and the smaller 1 minus v dash gets. So this is why we have it like this here. So you see it pretty much makes sense. And also if you take the color, the weight values like this, you also will see that they add up to 1, which means that they are valid values that we can use for a weight. So we see here how we can make a linear interpolation between these 4 values in 2D. Now, of course, the straightforward generalization to 3D is then from bilinear interpolation to trilinear interpolation. I didn't write down the full formula because it looks very confusing and scary if you see it first. But if you want to see it, you can look it up in the book, and it is pretty straightforward, especially if you write it like that, and you see that here you always have the color values. So in this case you have 8 color values because we're in a cube now. We end up with our UV function here, with our function in most likely in the center or somewhere inside of a cube. And then again we have, of course, in this case we have then 3 weights. We have v dash, u dash, and we also have w dash. And then again we see the closer it is to this value here, the larger these weights get, and in the other extreme we have u dash, v dash, w dash, c, 1, I plus 1, j plus 1, k plus 1, and that is this point here at the right side. So the further we get away from that, the smaller this weight here gets, and therefore the lower the influence of that color on our interpolated color value in the center. So that's pretty straightforward. It's just a lot if you write it down. But the calculation is actually pretty simple and intuitive, I would say. Good. All right, so we see now that how we can create 3D textures by calculating them. We also saw how we can create 3D textures by using a pre-calculated texture or pre-generated texture and then looking the values up by providing some sort of matching between them. But still, especially with the calculation, we've seen the examples that we talked about looked very regular or very artificial. Of course, they are regular because we are calculating them with some mathematical function, so there is some regularity with it. But of course, we can also model more complex, more realistic and natural values with mathematical functions. For example, like in nature, if you look in nature, if you create an artificial object, if you create a square or a circle, it has a regular shape. But if you look at structure in a real world, like if you look at a piece of wood or so, there is also some sort of structure, but it is kind of chaotic. So there is some randomness in there and some noise in there, but there is also some structure there. So for example, in fractal theory, what they're doing is trying to find this structure in more chaotic patterns. And this is also what we want to have in graphics. We want to, for example, be able to model something like wood that looks like wood, which has a certain structure, but each single piece of wood looks different. But if you compare wood, it has a certain characteristic. Same thing for things such as marble. If you look at the marble, like we have it here on the teapot, it looks random and chaotic, but there is some certain sort of structure in there. So how can we create these kind of things automatically with a mathematical function? So one of the ideas is, if we will say, well, if it's a random function, it's a random pattern, why do we not just create random color values? So we just do take the points that we have and then just create a random color. So for example, if we want to model wood, we just take different shades of brown and then we just take random colors. Of course, that wouldn't work because that would create too much noise. So that would create the kind of noise that you have on your TV, the white noise when you unplug the antenna. So, but like I said, wood is chaotic, but it has a certain structure, a certain feeling for it, a certain type. So The second idea is, well, we could say, well, then let's just create random points and then kind of smooth them out or try to put some structure on them, which can, of course, work depending on how much effort you put in, but the effort that you would need to put in is very high usually. So if you really want to create good results with this, this will be too computationally extensive. So the next idea is we could say, well, we could have something where we have certain kind of structure. For example, we could take the approach that we had. We can take a lattice and then create random values here and then interpolate between them. That creates something that looks a little better than these others. But the problem with this approach is that first, if you do a linear interpolation between them, you still have some sort of a regular transition between the colors, which can be visible in the final pattern. And also, if you have because of this grid or lattice structure, you always have color values, the maxima and the minima of the color values at regular corners. So if you look at the final pattern, then it will look like still you will see this kind of grid structure, because at each corner point, even if it's a different color, you always have the maximum and minimum at the corner points, and that can become visible in the texture. So how are we going to deal with this? And one way to deal with this is so-called Perlin noise, which is basically using certain tricks to deal with these three problems, which is why I listed them in the first place. So a lot of times in graphics, when we want to model something that is natural, but we cannot really calculate it straightforward, what we do is we actually use some sort of tricks or hacks to make it look natural, because the ultimate way to judge if a graphic is good or not is by looking at it and saying it looks good or it doesn't look good, or it looks real or doesn't look real. So a lot of time, if you go to the conferences and look about a graphics paper, you often see people showing some very strange algorithms, and then they say, okay, now if you compare this result, which is, for example, a piece of wood, looks better than all kinds of other models for wood that we have so far, so our algorithm is better. But it's sometimes you don't see it directly from the algorithm why it is better, and that's what I mean here by tricks. We just use some ways to just make it look good. And this is now this so-called Perlin noise, which we use for this kind of solid noise. In the book it's actually called solid noise, but most other references use Perlin noise for it, because Perlin is the guy who invented it. And this is basically just a set of ideas or a set of approaches to steps to basically deal with the problems that I just illustrated. And so let's go through it, and I'm trying to explain you not that much the mathematics behind it, but more the idea behind it, why we are doing these kind of steps. Because if you look at it first, it seems kind of strange, why am I going to do this? But if you think about what the problems are and what the characteristics of these steps are, then you realize, okay, this kind of seems intuitive why this might create a more realistic and more natural pattern. So the first step that we do is we create a random unit vectors we create a virtual 3D array of random vectors. So we create some random values to put some noise into our structure, into our patterns, into our textures. And you see here we use vectors and not values. And the reason why we use vectors is that we then do the inner product, which has certain advantages, which I'll talk about later. So we have grid values here, or a lattice with random values, and then we do an interpolation between them, like I said in the previous case. But you see here we do a different kind of interpolation, which has certain characteristics that makes it better, useful, or make more realistic results than the linear interpolation. So you see these are basically just some clever changes, and we'll see hopefully later why you will understand why this will probably create, or why these will create more realistic images. So let's go through the three steps. First, we said we want to create a 3D array of random vectors. Now, the major problem with this is if we create, first of all, how to create the random numbers, and secondly, how to store them, because if we have a very large texture, this uses up a lot of storage space, and this is why we're using here this why it doesn't say a 3D array of random vector, but a virtual 3D array, because it actually in the implementation is just a 1D array, and then we do a clever mapping between the two, between the 1D and the 3D, that kind of creates the illusion of having really a random 3D array, although it is just a 1D array. So but let's look first at how we get the random vectors that we want to have there. What we want to have there is we want to have random vectors that have a value between, that are on the unit circle between -1 and 1. So the unit circle is defined as we have here the origin 0, 0, 0, and then we have vectors that have a maximum length of 1, so they are all within this sphere, unit sphere, not unit unit circle, unit sphere, that are all within this unit sphere, and we want to have each direction with the same likelihood. So because we want to have random numbers, so each direction should be equally likely, otherwise we wouldn't have random numbers if one direction is more likely. And we can do this by just creating, of course, if we want to have a three-dimensional vector, we get 3 coordinates by just creating 3 random numbers. So we can create 3 random numbers between 0 and 1, but then if we want to have it on the unit sphere, we have to scale them to -1, be between -1 and 1. So we multiply them with 2 and then subtract 1. That gives us values between -1 and 1. Now the problem with this approach is, if you look at it here in a 2D case, if we do that, we can of course create random vectors in all kinds of directions, but they are not within the unit circle, they are within the unit square. And that means that here on this, if you take the extreme case where a vector points in a corner, in this direction you have much more options to create vectors than you have in the other extreme case, which is here, because this you have more distances, so you have more options to create vectors, which means if you create them randomly, there will be more vectors pointing in that direction than pointing in the other one. And to deal with this method, problem, we use a so-called rejection method, which is we just create the random vector and then we check the length. If the length is larger than 1, we just throw the vector away and create another one. And that way, we only take the vectors that are within the unit circle, which have all the same maximum length, which means that it is equally likely that we get a vector in each direction. So this is exactly what we want, and this is why we have to do this additional test here and throw away the other one. And then if you implement it, of course, you have to decide on how many vectors you want to create. And in the literature, you find that they often use 256. Now you want to probably wonder why 256. And this is, like I said, it just works. You just try it out, and then experience and trial and error shows that 256 is a value that produces very realistic results. And of course, you can take more, but then you run into efficiency problems. You want to keep the number low to be computationally efficient, but also you need to make it larger to make or the larger your number, the more random values you have, the more realistic your result looks. So you have to find a compromise, and trial and error and testing showed that 256 is actually a quite good value that is both computationally efficient and in terms of the quality of the results efficient. Good. Now with that we have a 1D array of random unit vectors, but of course we want to have a 3D texture, so we want to have a 3D array of unit vectors. Now we could of course just create a 3D array with that approach, but like I said, that would not be computationally efficient because we would have to create a lot of vectors, and most importantly we would have to store all those vectors. So what we do here is we just use a hashing function to create the illusion of having a random 3D array, a 3D array of random unit vectors, but in reality it's just a 1D vector. So maybe if you look at the image you can see it more easily. So what we have is we have created our 1D array of unit have an index I, j, k in our 3D. So this is the position I, j, k. This is the index in our 3D array, but since we don't have a 3D array, we have to take one of these values here, and we get that by, using a permutation of these values here from 1 to the length of the array G for each of the coefficients, and then we get one value here in this array. So you see, this is really, if we take then a value next to it, we might end up somewhere completely different. That's why we use these 3 permutations, and we use 3 permutations to make it really very much shuffled. So if we take the value next here, we might end up here, and then here we might end up very close to the other one again. And so it's really just shuffling the values around to create the illusion that we really have some random values in some three-dimensional array of random values here, although we just have a one-dimensional value. So it's really just a way to save the storage and to be more efficient. So we will see that it really looks like a hack, and that's basically what it is, but it's a very, very efficient and very clever hack that produces a lot of good results. So we have our 3D array now, and of course then we want to have the same as before. We have a UVW value, and then we have a pointer to a position, which most likely is not directly one of the index corners here, but is somewhere within this cube. So we have to decide what kind of value do we assign to this point here from the 8 nearest neighbors here. And so we could do this by just calculating the linear a weighted sum of those with the interpolation, but also for the points here, like I said, if we create this pattern and then we create here random values and then interpolate between them, we always have the max and minimum at these corners here. So if we then do create the texture by this with the linear interpolation, we see the maximum and the minimum values still, the local maxima and minima, we still see the grid structure there, which is why we kind of modify these values with this noise that we created here. And we do this by using the creating the inner product of the vectors. And this is again, this is exactly the reason why we created here random vectors and not random values, because if we would just take the values, then we would stick to this local maxima and minima at the grid structure. But what we do here is we have here the random vectors for each entry, for each index entry, and then we multiply that with the vector that points towards our UVW value. So here between these two vectors we take the scalar product, and that means we get one value here. So for each of the corners we get now a random value, which is not this original random value but slightly modified. So we basically shift this value a little bit to the side, and then we have here the random values, and then we can do the interpolation. And now you see the other problem was, of course, even if we like shift the local maxima and minima a little bit here and then do a linear interpolation between them, we still get this regular interpolation between them, which looks very regular, like if you I draw it later. And this is why we're using this Hermite interpolation, which looks a little scary at first, but if you compare this to the linear interpolation, you will see that it's pretty much pretty straightforward, and there are only minor changes here. So this here is the sum over all the 8 corners of the cube that we have. If you write it down, you will see that these are just the index. If you write it out, you will see that these are just the index values I, j, and k, and then over all the 8 corners that we have here. So for each color value, in a linear interpolation we had it for each, in a tree linear interpolation we had it for each color value. Here we have it not for the color value, but we have it for this scalar product, which is exactly what we produce here in the second step, which is our random value. We we sum that up over these values with a weight like we had previously, but now we do not have a linear weight. But if you look at the weight function here, you see we have t to the power of 3 and to the power of 2. So we have a cubic weight function here. And Perlin claims that this produces better results. Now, if you look at how a cubic function looks like, it's kind of intuitive to understand why this might produce better results. So if you look at the linear function, w and t, then the weight is proportional to t. So if this is again our color 1, this is our color 2, and this is now a particular t point, where this is the fraction multiplied by t, this is the fraction multiplied by 1 minus t, then you see, of course, when you move t to the right side, the fraction of this color, of the overall color, increases, and the influence of the fraction of the other color decreases. So this is how we had the linear interpolation. And of course, you can imagine if you do this with grid points that this sometimes creates some color that is visible in your texture, so it doesn't look like this marble structure. But if you look at the cubic function, which looks like this, if we have our color here, our colors here, color 1 and color 2, and now if you look at what happens to t and t minus 1, if we increase it, we see that the color, the influence of the second color on the weighted color, the sum of it, first is very, very slow, and then it's about linear in the center, and then the influence becomes much lesser, and this the influence of the second color increases much stronger towards the point here, which means basically we get a smoother transition towards this local maxima and local minima that we have here at the corners. And this is basically the Perlin noise, and like I said, it looks like a very straightforward set of rules, but if you think about what each of these rules does and why we do it, because of the problems we identify in the first place, it kind of feels you kind of understand why we're doing this, or it kind of starts to make sense. So to summarize the steps, we first create a virtual 3D array by using a 1D array and a hash function, which is just the major motivation for this is to get the random value vectors and to store them efficiently. Then we do the scalar product of the random with the random unit vector and the Hermite interpolation. The scalar product of the random unit vector, if you think about it in 1D, you could illustrate it like this, that you say, if you create at each position a random value like this here, and then do a linear interpolation between them, of course, it is very likely that you see in the final pattern these local maxima and minima because they have such a regular structure. Now, what the scalar product with this random unit vector does is basically it shifts those local maxima and minima a little bit. So let's say this one shifts here, this one shifts here. And since they're random, they shift in different directions. This one shifts here. And now, if you would do a linear interpolation, you would still have situations where you see this structure because it changes at the same way, which is why we do this Hermite interpolation, which is then something like this. And you see also now here, if you would not shift the local maxima and minima and would just do a Hermite interpolation here, we would still have some sort of a regular structure. And if we would only shift the maxima and minima and do a linear interpolation, we would also still might see some regular structure here. But by doing both together, it is very likely that we get a more chaotic structure, that we don't see much regularity, but still we have some regularity in there. And this is exactly what we want. We want to have structures that are somehow regular, but somehow not regular. So this is, and with this function we can actually create a lot of interesting textures. We can use that to create wood, we can use it to create clouds or these marble structures. So if you Google, do Google image search on Perlin noise, you get all kind of very interesting and nice textures. And this is also a very fun thing to implement and then play around with the parameters and see how it changes and what you can really create by changing the parameters, which is why this was actually part of last year's second practical assignment. But we decided to leave it out this year because we realized a lot of people have problems with it. Maybe we will have it in the third assignment as one of the third practicals. Don't remember. We'll see. All right, yeah. So you're safe from it now, but might need to do it in the future. Good. All right, then I think it's time for a break.